Good morning, students. Welcome to Commutative Algebra lectures. In this lecture, we'll discuss about modules over a given ring. Okay, so let's start with. Before starting the definition of a module, we are already known about a known concept called a vector space. So we'll just quickly recall this what is meant by vector space so that we can easily understand what is a module. So a non-empty set V, if you take, is said to be a vector space. Is a vector space, of course, over this is important, over a field F, or a field F, if roughly speaking, if this vectors can be two vectors can be added, and a vector and a scalar, this elements of this V, we will call it as vectors. Okay, and these elements of this F are called scalars. So if two operations are there, V cross V to V, so this you can call it as addition, and scalar multiplication, V cross F to V. Okay, so obviously how this will be, x plus y, okay, should belongs to V, and x times a, where a is a scalar, should belongs to V. So if these two operate with respect to these two operations, of course, because here uh, you can have, because it is a field, if you take two elements a plus a and b from the field F, then what can you say about this one? This should be same as how we can expect. You take xa and xb, these two are elements of v, then you add them. Okay, similarly, whether you take, because it's a field, you can multiply two elements also. Okay, this should be same as x times xa times b. Okay, and other properties, right? So if these conditions are satisfied, then we say it is a vector space over a field F. Right? Now, a module is similar to this concept. What in fact it is more generalized than a vector space. So a module is nothing but, here what we are taking here is over a field. Okay, but if we replace this, so if we can replace this by a ring, okay, then ring, you can call it R or A, whatever, then what we get here is called a module, right? So that is the concept of a module. So we can see here, let A be a commutative ring. So now, as throughout this uh, lecture series, we will consider a commutative ring with unity. Okay, then you take any abelian group M. So A is a commutative ring, A is a commutative ring, and M is an abelian group. Okay, if you take M is a non-empty set, then you have to say that M comma plus whatever operation we are taking is an abelian group answer. Okay, this is called an A module. So this M is called module over A, or a module, if there exists a map. So precisely what you can, this one is same as scalar multiplication. This you can call it as a scalar multiplication, right? Scalar multiplication in this vector space. Okay, that same map, it should satisfy these properties which we have seen already, right? So whenever there exists a map from A cross M to M satisfying these conditions, then we say that this M is called a module over A, or simply a module, right? So the advantage here is, our base whatever we are considering, this is a ring, right? Whereas in a vector space we require condition to be field, right? So we can see some quickly some examples that what are all modules one can have. If you take A is a ring, right, then in a ring we already know that if you take A is an ideal. Okay, so we have already what is by definition of ideal itself, if you have some x in a ideal and A is in a ring, then we know that x times A is again in that x times A, sorry, this is x times A is again in that ideal, right? Okay, so that itself shows that when you take the map A cross this to this itself, we have a map, and it you can easily check that it satisfies the properties. Okay, so therefore every ideal is actually a module, right? With this, by definition itself, every ideal is a module, right? Now obviously if your ring A is a field, okay, so if a ring becomes a field, then what we have, a module is same as a vector space. That means any vector space is a you can is nothing but a k module, as k cross v to v, it is nothing but simply scalar multiplication. Okay. Now if you take a ring, known ring A is equal to Z, this is a third example. If you take A is equal to Z, then you can see that any abelian group, if you take any abelian group M, will become a module over Z. So any abelian group M is a Z module. Why? So that means we should able to define a map from where to where. We should able to define a map from Z cross, if you call it M or G, whatever you call it. So this G is our abelian group. Okay, G to G, right? Obviously, if you take any n here and an x here, we have to define in such a way that this always belongs to that group again, right? We know in group we can add two elements, okay, and every element has inverse, additive inverse, and so on, right? So n is a natural number, is an integer. So if at all n is greater than or equal to 0, then nx has a meaning adding x x x n times, right? Whereas if n is less than 0, then you add minus x n times. So this is n times, okay, minus x, okay. So you add minus x n times, but n is less than 0, so what you get is that again same thing, right? So if n greater than or equal to 0, then nx is same as adding x n times, and if n is less than 0, nx is same as adding minus x n times, right? So therefore this map is clearly well defined, and hence any abelian group is actually a Z module, right? And there, these are other some examples, one can go through it. Now we'll see if we have, suppose M and N are two A modules, okay, where A is a commutative ring, then we can define a homomorphism, module homomorphism. F maps from M to N is called a module homomorphism, obviously because these are abelian groups, so you can expect x plus y, it should be same as f of x plus f of y. And with respect to that scalar multiplication, if you take a times x, it should be same as a times f of x. Remember, M and N are both a module homomorphisms, right? A module homomorphisms, okay. So therefore f of ax is a times f of x, it should be, right? If these two properties are satisfied, then such a map is called a module homomorphism. Okay. We all know that if that ring, our ring A is a field, then this module homomorphism is simply nothing but linear transformation, right? Because we know already a linear transformation satisfies these two conditions, right? Okay. And you can define composition and all, it is not a difficult one, right? If you have f maps from M to N, okay, and you have N, this is F and this is G, from N to P, then composition you have, okay, from M to, there are also modulo homomorphism, right? You can easily check, this is not a difficult one. Then now you take M and N are two A modules. So suppose M and N are A module. Now collect this all uh, from M to N such that F is a homomorphism. Collect all collection of homomorphisms from M to N. You denote this by hom M comma N. Okay, of course over E. Then you can see that over this you can define a module operation, namely if you take f and g are two belongs to here, that means they are module homomorphisms, then how you can define f plus g of x is obviously f of x plus g of x, okay. Then a times f of x is same as a into f of x, right? You can check that with respect to these two, this is again an a module homomorphism. So therefore if you have M and N two A modules, then we have another module which is namely home M comma N over A, right? Okay. And another thing which also useful in our further lectures is, suppose if you have F maps from M to N is a module homomorphism, okay, and you take any another homomorphism, you can call it U, from M prime to M. Okay, then if you consider this homomorphism, it induces a module homomorphism, you can call it u bar. Okay, from home m comma n to home m prime comma n. Okay, so how you can given by u bar of, if you take any f here, which is a homomorphism from m to n, how we should able to define such a that it should be a map from homomorphism from m prime to n. So you can easily check that if you have f and u, so you first go from u then f, so that means this f composed u, right? Clearly this you can check that this belongs to this home m prime comma n. Similarly, when you have from n to n prime, this also induces another homomorphism v bar from home m comma n to home m comma n prime. So you, whoever know about this, you can replace this by first as well as second place, right? Okay, so this is v composed f, the first one is f composed u, right? One can easily observe that if for any a module m, if you take all homomorphisms from a to m, okay, this is precisely isomorphic to m itself, right? So the m is an a module, this is also an a module, but these two are isomorphic. Okay, that means we should able to define a map. Okay, this is a isomorphism as modules, right? We have to define from home a comma m to m, right? And show that it is a homomorphism bijective. Okay, then it will become an isomorphism. Obviously, if you take any f which is from a to m, how we can, so you have f maps from a to m, right? We have to define in such a way that this should belongs to m here, right? We know a is a commutative ring, so f evaluated at value 1, because we know that this commutative ring has identity. So you define psi of f as f of 1. That means you take any homomorphism f from a to m, then you evaluate that function at 1. Then whatever value that belongs to m, you can easily check that it is a homomorphism. Okay, so one can check that it is a homomorphism. It is not really difficult. Check that this psi is a homomorphism. Then you can easily show that it is 1 1. That means psi of f is 0. Then you show that f is 0 itself, and it is how we'll show that it is injective surjective. So take suppose some m in m, right? Then we want to somehow for this m we want to define a homomorphism from a to m. So you define, you call it that as g of m, which from a to m, in such a way we have to define such that gm, you take any a, right? So obviously what should be, a is in a and m is in m. So if you take a times m, we know that it is again in m, because m is an a module, right? With respect to this, you can check that what is, now our idea is to show that we want to there should be a homomorphism which maps to this, right? Okay, so then you can check that this gm, then gm is a homomorphism, so therefore this belongs to here. And what is this psi of g of m, right? How this psi map is defined is simply evaluated at value 1, right? So therefore this is gm of 1, but gm of 1 is a times 1, which is a, right? So sorry, a times a is 1 here, so 1 times m, so this is equal to exactly m. So therefore our map psi is onto, so it is bijective, and you can easily check that it is this map whatever we have defined. By the way, it is simply f plus g is f of 1 plus g of 1, so it is a homomorphism, right? Therefore home a comma m is always isomorphic to m itself. Now we'll define submodules and what are all different operations are available on modules and so on. So you take any subset m prime of given a module m, which is an a module, right? Then we call it this uh, if m prime, if it is a subgroup, so any subgroup of m is called a submodule, right? So m is an abelian group, right? You take any subgroup, then subgroup of that m we will call it as a submodule of m. And if you have subgroup, then you can talk about m modulo m prime, this as x plus m prime cosets. Okay, and you can, with for this one we can define two operations, namely these are the two operations which is not a difficult one. Okay, x plus just like coset operations, right? Then you can check that this m modulo m prime with respect to these two operations is an a module, right? And you can call it that as quotient module. Okay. Similarly, any submodule, if you take m modulo m prime, how any submodule look like here? Look like m double prime modulo m prime, right? Where m double prime is a submodule of m, okay, and containing m prime, okay, right? So in quotient modules, what are our submodules? Are nothing but of the form m double prime upon m prime, where m double prime is a submodule of m containing m prime, right? Then you can easily if we have f maps from m to n a homomorphism, then we have another submodules, namely you take kernel of f, okay, which is a submodule of m. Then you take image of f, which is submodule of n, and co-kernel of f, which is n modulo image of f. So this is nothing but this is quotient module, right? uh, okay. Now, what are all different operations we can have it on modules is sum of submodules. So if we take MIs, which are all submodules of M, where M is an A module, okay, then we can define what is meant by summation MI. I is from 1 to n. So what should be the guess? Simply summation xi, where each xi is coming from mi, right? If we take this one, then it is the sum of n modules, which is again a module. What should be the map? A cross summation mi to summation mi we require. We can easily check that this a times summation xi you simply define as summation a times xi, right? So with respect to this map, you can easily say it is a again module over a, right? We can also define an infinite sum, summation mi, I is from 1 to infinity. Obviously, it cannot be infinite sum, so we xi from I is equal to 1 to infinity, but except finitely many, all xi's are 0. So such that all xi's, so xi's is equal to 0 for all, but except finitely many. That means every time, every element here is a finite value. Okay, sum of finitely many elements, right? Okay. Then if m1 and m2 are two modules, or mi's are two modules, then intersection of this one, right, is again a module. You can check that. So this, and with respect to this operation, it is not difficult to check, right? This, if we have this summation sum of mi's and intersection of mi's, then we can observe that this sum of mi's is a module, which is this smallest module containing, because we know each mi, so each mi sorry, so if you take mi, then it is contained in sum of mi's, okay. So therefore this summation mi is the smallest one which contains each of the mi's. And if you take intersection of mi's, okay, we know it is contained in each mi, right? So that therefore this is the largest one which is contained in every module, right, mi. Okay. And now we will see some interesting results. Like you take L, a module, okay, and M, and then N. That means N is a submodule of M and M is a submodule of L. So obviously N is also a submodule of L, right? Okay. So you can talk about L modulo N, right? Similarly, M modulo N. Now you can check that whether M modulo N is a submodule of L modulo N or not, right? Why? Because M is contained in L and containing N, right? So therefore this one is a submodule. So M modulo N is a submodule of L modulo N. Therefore you can talk about its quotient, and we expect that this should be isomorphic to L modulo M, because M is a submodule of L. Okay. So this, if you understand this one, then defining a map is not at all difficult. Obviously, how we will define? We will define a map from L modulo M to L modulo N, then L modulo N to L modulo M, so that kernel is precisely this M modulo N answer. Okay. The other interesting property is that if we have two modules m1 and m2, then you take m1 plus m2. We have just now seen that m1 plus m2 is also a submodule, right, containing m1 as well as m2. So because it contains m1, we can talk about modulo m1. This is isomorphic to m2 modulo m1 intersection m2. Okay, there is nothing special about this m1 here. You can also replace this by, if you replace this by m2, then what you will get here is m1 modulo m1 intersection m2. Okay. Fine. So these are all again proving homomorphisms. We all know the standard trick is try to define a map so that it is a homomorphism, and show that kernel is precisely what we are looking for, right? So for example, from L modulo n to L modulo m, define f. How? F of, if you take x plus n, you define simply this as f of this x, okay, because it is again in L only. So x is in L, x is in L. In play, we want this one, x plus m. Then you can check that kernel of f is precisely m modulo n and so on. It is a surjective homomorphism, right? So basic calculations I skip. Similarly, from m2 to m1 plus m2, this you can define simply send inclusive map. It is actually it is an inclusive map, and define from m1 plus m2 to m1 plus m2 modulo m1 by this way. Okay, g of x plus y is y plus m1. Then you take the composition, which is a map from m to this, and show that kernel is precisely the intersection, right? So that this is not a difficult one, but those results we use frequently again and again, right? Now when we have seen some of the ideals, intersection of the ideals, quotients and so on, but one can easily see that we may not able to define what is meant by product of ideals. See, suppose if we have m1 and m2, right, we don't know how this product look like, and what is this a cross here to here, how whether we get or not, it's not clear, right? So product of modules may not be defined. It may not be a module again, but if we take you take a is an ideal of given ring a, and m is an a module, okay, module over a, then we can talk about this a times m. Okay, this is obviously precisely summation, uh, this is precisely summation xi yi, where xi is in the ideal and yi is in the module m, right? Is, you can check that this is a submodule of m, this is a submodule of m. Okay, now you can define, suppose n and p are submodules, okay, of m, then this n, you can call it just like a divided by something like this, okay, is all x belongs to a ring such that x times p is contained in n. Okay, just like x times p is it should be a submodule of n, right? Then you can check that it is an ideal because it is a subring subset of a. We can show that it is a clearly an ideal of a. Okay, right? So once this is an ideal, then you can define a module when we say that m is an annihilator. This annihilator of m, you can define this as this 0 m. That means all the elements of the ring such that it which kills m, a times m is 0. Okay, right? And if annihilator of m is precisely 0, that means 0 is the only element which kills every element of m, then we say that this m is called faithful. Okay, so this m is said to be faithful, a faithful, if annihilator of m is 0. Okay, if annihilator of m is non-zero, then because it is an ideal, you can talk about this a modulo a, where a is any submodule of this, okay, containing here. You can see that a is faithful if annihilator of m is 0, and if annihilator of m is non-zero, which is an ideal, then m is actually a modulo a, where annihilator of 1, okay, this faithful, because here in this ring this annihilator of m is 0. Okay, fine. and one can check that this is annihilator of m plus n is intersection of annihilator of m and annihilator of n, and this n colon p, this one is nothing but, it is an ideal, it is nothing but annihilator of n plus p upon n. Okay, now we quickly see what is meant by finitely generated modules. Okay, so as it suggests, you take m is an a module. Okay, and suppose take ax is any m, then what is meant by this ax is all elements generated by x, right? You can call it in this way, this is nothing but a times x, where a is in a, right? So if m is summation a xi's, okay, then this is x1 x2 xn is called generating set, right? So if any x in m, if we can write there exist, okay, ai's in a, right, such that x is summation ai xi, then this x1 x2 xn is called generating set for our module m, right? Now m is said to be, a module is said to be finitely generated if there exists a finite generating set. Okay, this, that means any m can be written in this way, then we say it is finitely generated, right? Then we can also define another type of two modules. One is direct sum and direct product of modules. This is direct sum and this is direct product. Okay, so they are actually tuples, only operation is different. So you take direct sum of mi's is nothing but this tuple, it is sequence xi where I is in a, where xi's are belongs to mi's, but finitely many are 0. That means except finitely many, remaining all are zeros, right? Similarly product of mi's, then the operations are simple. Okay, you can check this one, right? Okay, so only difference between this direct sum and product is, in direct sum we require that except finitely many xi's, remaining all should be 0, whereas in product mi we don't require any such condition. Okay, so obviously they are equal if your indexing set is finite. If your indexing setting is finite, then these two are actually same, right? If one can observe that this one is always contained here. Okay, direct sum is always a submodule of direct product, right? Okay. Now I can skip this. We say that a module m is said to be free module, okay, if m is isomorphic to direct sum of mi's, where each mi is actually a copy of a. That means if you can put m as direct sum of copies of a, okay, where I is an indexing set, then we say that it is a free module. Okay, so again a module m is said to be free if m is isomorphic to direct sum of mi's, but each mi is again a copy of a, right? So if you can write direct sum of copies of a, then m is called a free module, right? Then a module m is said to be finitely generated free module if m is isomorphic to finitely many copies of a. That means m is here, only difference between this one and this one is that I is should be a finite set, that's all, right? Fine. Now we'll see some proofs, results related to finitely generated modules, right? So you start with M and A module, then M is finitely generated A module if and only if this M is quotient of, okay, that means M is isomorphic to quotient of some M A power N, right? So you can, how you can write this? So this M is the quotient of free module A power N modulo something. Okay. Proof is not difficult because m is finitely generated, so we have a generating set x1 x2 xn be the generating set. Then you can define a map f maps from an to m. Okay, simply f of, if you take a1 a2 an, then because for this m you have already generating set, so therefore we want to send it to unique element, so you send it to summation ei xi. Okay, then you can check that it is a homomorphism, and precisely what are the kernels, right? uh, that means what is kernel of this f? Kernel of this f is nothing but this ai's, right? This a, you can call it a, which is nothing but a1 a2 an, such that the summation ai xi is 0. Okay, now because it is a module homomorphism, you can check that it is a clearly a surjective map. This f is surjective. Why this f is surjective? Why this f is surjective? Because if you take any x, then we can write this as x can be written as summation bi xi's, where bi's are in a and xi's are in that m, right? That means this f of b1 b2 bn is actually nothing but our x, right? That shows that this is a surjective homomorphism. So therefore this an modulo its kernel is actually isomorphic to m. That shows that m is a quotient of this a power n, right? Conversely, if you have an onto homomorphism, that means m is the quotient of am, that is same as saying that it has an onto homomorphism, then we can show that its m is actually finitely generated. Okay, so right, m is finitely generated. We want to show it. So you take any x in m, then using this surjective homomorphism, there exists a1 a2 an, that such that phi of this is 0 equal to x, and simplify this and you will get that x is equal to summation ai phi of ei. Okay, that means this phi of eis, they are actually generating set for m. That shows that m is finitely generated, right? Okay, now let's move on to another result. If we take m is finitely generated a module and I is any ideal of a, okay, suppose if you have an endomorphism phi maps from m to m, okay, such that phi of m is contained in I times m. Okay, we know what is meant by this I m, we have defined already. If these conditions are there, then there exists some n such that this phi satisfies this equation. Okay, an equal to 0. Remember, this is a map. So when you apply any element to that, it should be 0, right? Proof is not at all difficult one. We have to use the fact that phi m is contained in im. So if you take any x in m, right, because m is finitely generated, then x1 x2 xm is generating set, right? So and each phi of these xi's belongs to im, and any element here can be written as summation finite linear combination. So therefore phi of xi's, you can write each phi of this xi can be written as summation aijxj. J is from 1 to n, right? Then using this delta ij, which is 1 if I is equal to j and 0 if I is not equal to j, then you can simply write this expression as summation j is 1 to n delta ij phi. That means it is system of n equations we have, right? So therefore we can write this of the form bx is equal to 0, where b is delta ij phi minus aij, that is precisely this. Okay, diagonal entries involves this phi and remaining all are this ais, and x is x1 x2 xn. Okay, then by simple calculation by multiplying adjoint, then you get inverse. Okay, determinant. So mod b of x is 0, that means for all I, mod b times xi is 0. Okay, but xi is nothing but the generating set, right? So therefore an any m, if you take mod, this one is 0. So therefore this mod b m to m given by mod b of x is 0, therefore it is a 0 endomorphism of m, right? Now if you find this determinant of b, whatever we call it, you get that if you expand that, this is 5 power n plus a1 5 power n minus 1 plus an equal to 0. Okay, so what it says is the result is important, that if m is finitely generated a module and we have an ideal such that phi of m is contained in I times m, then there exists some n such that phi n plus a1 phi n minus 1 plus and so on equal to 0. Okay, so as a corollary, we can prove two results. One is if m is finitely generated, okay, and I is an ideal of a such that I times m is m, okay, then there exists some x which is congruent to 1 modulo I, such that x times m is 0. Okay, so x kills that m, right? And x is congruent to 1 modulo I, and it is precisely, it follows from the previous result. You can simply taking the identity map, okay, then it is an endomorphism, and you can check that phi of m is m, so which is clearly contained in I times m. So therefore there exists some n satisfying this, and by taking x is equal to 1 plus a1 a2 an, you can check that these are all AIs belongs to the ideal. So therefore this is congruent to 1 modulo n, 1 modulo I. Sorry. Okay, because this much part actually belongs to that ideal, right? Okay. Uh, one interesting result called Nakayama's lemma. We can prove this using this result. What it says is that if you take M is finitely generated A module and I is an ideal which is contained in J, where J is a Jacobson radical. Okay, this is Jacobson radical. Okay, then whenever I times M is actually equal to M, then M has to be 0. Only possibility is M should be equal to 0. Okay, so here I times M is equal to M. By using previous corollary, there exists some x such that x is congruent to 1 modulo I and x times M is 0, right? But x is congruent to 1 modulo I is same as saying that you can write as x is equal to 1 plus a for some a is in belongs to I, but a belongs to I is contained in J, so therefore a belongs to J, and J is a whenever J is an element of Jacobson radical, then 1 minus a times any element of that idea ring is a times b. This is an unit, okay, for every b in A. So in particular, if you take b minus 1, then 1 plus a is a unit, right? That shows that x is a unit, right? So if x is a unit, then by multiplying x inverse, what you get here is m is 0, right? Using this, without using this corollary, you can simply prove it directly also. We want to show that m is 0. So suppose m is non-zero, then m is finitely generated, so therefore we can have a minimal set of generators. So we will denote that minimal set of generators by u1, u2, en. That means you cannot have you cannot generate m less than these fewer elements, right? But we'll get fewer elements which is a generating set, that will be a contradiction, so therefore m has to be equal to 0, right? And this is not at all difficult one. This m is equal to im we will use, okay, and each un belongs to m, right? Each I belong ui belongs to m, so therefore it belongs to I times m. So un we can written as combinations of these ais uis, and use the fact that using Jacobson ideal an belongs to here, it is a unit, so multiply this. What you get here is un you can actually write as linear combination of u1 u2 un minus 1. Okay, so that means actually un is not required for generating that set, which is a contradiction, right? So that is a famous result of Nakayama's lemma. Okay, and one more corollary. What it says is that if you take M is finitely generated A module and N is a submodule of M, okay, and I is an ideal contained in Jacobson radical, then I times M plus N, if at all it is equal to M, then N should be equal to M. Okay, so what we show here is we will use Nakayama's lemma. Somehow we whenever we want to show n equal to m, you consider this m modulo n. Show that this is equal to 0, then m should be equal to n, right? Okay, so how we will show m modulo n is 0? We apply this Nakayama's lemma. So if we want to show that to apply Nakayama's lemma, what we require is I times this here. If we want to apply Nakayama's lemma, we require that I times m is m, then m should be equal to 0, right? Okay, so you can apply that and show that I times m modulo n is m modulo n. Then what we get here is that is same as show that these two are equal, and it is not a difficult one. Using a simple coset operations we can show that. Okay, so therefore m modulo n is 0 is same as saying that m is equal to n. So this precisely follows from Nakayama's lemma. Okay, so some other properties we'll see in next class, so we'll stop here.